Morning, AP chemistry people. We need to talk some more cell potential and all that kind of stuff. I know you might be distracted by this beautiful mustache I like this thing way too much. I'll make myself really small so you can barely see. It won't be so distracting then. So we need to talk a little bit more about electromotive force today and voltaic cells and all that kind of stuff. So EMF is basically cell potential, that's voltage. You've already calculated that a few times. The book really likes this the reduction potential at the cathode minus the reduction potential at the anode. That is also how OWL will tend to do that. They'll say, oh, you've got to do this. I just view it as Hess's law, right? When you add them together, just like if we add together the delta H's for reactions, you have to have them in the right direction. And when you flip them, you flip the sign. Well, the reduction potential at the anode, remember the vowels together, anode, oxidation. What's happening at the anode is oxidation. Well, the reduction potential when it's being oxidized, well, that's flip, right? So I just view it as write them as they actually are happening, and then you add that together. But the book likes to do it this route. And I've had some students who write out the equation and plug them in that way. And that's absolutely just fine. That's the way the book likes to do it. It just makes more sense to me to write them as they're actually happening and realize that the thing that they're giving you is a list of reduction potentials. And I think I've got those, like here, right? This is written as a reduction. So if what's happening is an oxidation where it's going the other way, right? Like iron is being oxidized to Fe plus 2, well, that's going to be a positive 0.45, right? We did a couple of those already. I don't know that we need to do a bunch more of those and stuff, but the tough part really on those galvanic cells is just figuring out who's being oxidized, who's being reduced. Remember, delta H is E, electromotive force, is opposite of delta G and delta H. A positive is spontaneous, a negative is non-spontaneous. So electrons are going to flow in the direction that makes the whole thing a positive E, not a negative E. If we think about stuff like in terms of batteries, right? When I go out and use my little electric weed whacker, that's an electromotive force. The battery runs, gives me voltage when it runs low on juice because the chemical reactions are pretty close to being done. There's no more no more electrons to transfer over. I hook it up and I force it to run backwards. So when it's being forced to run backwards, I'm putting that energy back into it and it's running in the opposite direction. To make one rechargeable, that's more of an engineering than a chemistry thing. Any battery is rechargeable from a chemistry point of view, but if you don't design them sturdy enough to handle the heats and all that kind of stuff to get involved with that, then they explode and stuff. So you can take a regular old Duracell and stick it into a battery recharger and it will recharge it, but there's a good chance that it's going to explode. Not like hydrogen bomb explode, just like, and then battery acid, which is very concentrated acid, is all over the place. So you might hear about people doing that at some point and they're like, oh, every battery is rechargeable. You're not wrong. You're just dumb because the engineering of those batteries is not designed to withstand that. So you're going to get battery acid on stuff, and that's not ideal. All right, this is going to get long if I don't move forward. So let's work with a. Wait, am I doing this one moving forward? Because we've already done that. Yeah, concentration effects. So let's say we've got a standard zinc copper cell. So we have zinc. Should we grow this? Is that going to be big enough for you to see if I grow this and work off to the side? Right, so we're going to have zinc to zinc plus 2, salt bridge, copper plus 2 to copper, right? That would be our line notation. Maybe I need to bring this closer so that my right extra big, and I'll turn the lights off maybe. Can you see that well enough, or are we going to start lagging now? Okay, so we move forward on our slideshow. This is our reduction potential, and we've already used this some. We just need a zero because it's all about change. So we just need a spot to say a zero. So they define the hydrogen one as 0, and then things are positive and negative based off of that. So we find the zinc and the zinc plus 1, well, that's a negative 0.76. But if you look at it as I have it written here, you have zinc going to zinc plus 2. So I'm going to flip the sign and do a positive 0.76 for this half of the reaction. And then we find the copper plus 2 going to copper, and that's a positive 0.34. Hey, that works out. You've now got a positive 1.1. If I had written this backwards, if I had written this backwards, we would have ended up with a negative 1.1 here, and then we've written it in the wrong direction. It's kind of a self-correcting problem, right? But I do need to go back and rewrite it then. So I have zinc going to zinc plus 2, salt bridge, copper plus 2, going to copper. These are in a different phase, so we have to do that, and then I'm indicating my two-phase shift with my salt bridge there, right? So look this up so I'm not quite so in your face. But what if it's not 1 molar? This is for standard conditions, just like 22.4 liters per mole is only for a gas and only at STP. This is only at standard conditions, which is 1 molar and 25 degrees Celsius. Standard temperature is different than with this kind of stuff. And we'd never really see temperature stuff change. At our level. In real life, do batteries get warm while they work? Absolutely, and they're not as efficient. The numbers the voltages go down, which is why it then gets harder to work and it burns up its own battery faster when it's hot. And you should, if you're having issues with that, you let it cool off for a little bit and stuff. But if your cell phone in general is sitting around getting hot, it's because it's using more battery power than it needs. It probably has a bunch of viruses and stuff on it. So not as big a problem now as what used to be like 5-6 years ago. You used to see that quite a bit. So people's cell phones would just sit around hot because they had so many viruses on them and stuff. I don't really hear about that now. Anyway, but what if you're not at 1 molar conditions? You already played with this a little bit in the simulation on Friday. Just from an equilibrium point of view, you can get a shifting. And this is one of the things that I used to introduce with a physical lab we do. We used a very dilute silver solution and a pretty concentrated silver solution. And you would actually get electrons flowing just to try and balance out the concentrations of the solutions, right? Just kind of an equilibrium thing. Where's my mouse? Hello, mouse. Why aren't we working? Okay, video might be really laggy there. Anyway, so you use the Nernst equation. It's really fun to say. It's not as fun as Le Chatelier's principle, but it's the Nernst equation. That's kind of silly sounding. So you take the standard cell potential, which is what we've been calculating, minus 0.592 volts over N. There's a significance to that 0.0592. I can't remember what that is. It's something to do with logs or something, but that number pops up occasionally, right? But that's one you'd want to, I think that's on the back of your periodic charts, but if not, you'd want to write that down so you have it handy. Times log of Q, where again, Q is like an equilibrium Q. I said the equilibrium word. I know people are like throwing their Chromebooks across the room right now. It's not actually hard. It's actually pretty easy. All you have to do is the solution-y part of the products over the solution-y part of the reactants, and you plug that in here. And the solids, because they're solid, get left out, right? How big my copper electrode is doesn't matter. It's the concentration of the solution that matters. So let's pretend I did this one, but I had... let's say the zinc is 10 molar and my copper is 0.01 molar, right? Let's say we've got that situation. So if we do that, then to solve for that E, I would do my E standard is positive 1.1. Let's write that bigger so you can see it. My E is 1. So it's a positive 1.1 volts for my standard cell potential. Then I do that minus 0.0592 over N. N is the number of electrons that change from here and here. So it's the number of electrons in my balanced redox equation. So while we get to ignore N when we're doing our standard cell potentials, when you get into the Nernst equation, the number of electrons does end up being something that matters there, right? So we have 2 electrons transferring here and 2 there. So my N is just going to be 2, right? It's whatever the number of electrons in your balanced redox equation would be. So that's a 2 there. And then that's going to be, we're going to multiply that by log of 10 over 0.01. It is really easy to see what my products and reactants are, right? Q is products of reactants. Well, the reactants are the first ones that we write. The products are the second ones that we write. Well, that's a solid, and that's a solid, so I can ignore it. So it's just going to be zinc, which is 10 molar, over copper, which is 0.01 molar. Well, that's 3 powers of 10. So log of 1,000, log of 3 powers of 10 is just going to be 3. So 3 times 0.0592 divided by 2 is going to give me 0.0888. So it's going to be 1.1 minus 0.0888. So since I had a lot of products and not much reactants, it gives us less voltage. Right? So that's going to lower my voltage there. And so my voltage is going to basically work out to be 1 now, 1.1 minus, I don't know let's see how many sig figs we should keep on that. We can only keep 1. Or well, 2 to the 1's place, or to the 10th place there, 10th place. So 1.0 volts. So if we imagine kind of how this plays out in batteries, it makes sense, right? It doesn't make a big difference, right? Even when you're pretty significantly different in concentration, it doesn't make a huge difference, but it does make a difference. And once those concentrations gets real different, then it's going to start to make a bigger difference. And that's why you start to see things with rechargeable batteries start to lose some power, but not through most of their life. So this Nernst equation matters, but it's not going to make a big difference until those concentrations are significantly different, because it's a base log kind of thing, right? So here's a nice little one that you could do on your own there, right? So if we have a concentration of 5 molar and 0.05 molar, just stop and think for a minute. Is this going to raise my voltage or lower my voltage, right? What's my product? What's my reactant? Well, my reactant is the copper and the product is the zinc. Well, now the zinc is at a low concentration, so that's going to make it kind of easy for that to transition to it. The copper is my reactant, so it's going to make it easy to get more copper. So this should raise my voltage a tiny bit, right? So without writing the whole thing out, but giving you a quick, so you do 5 divided by 0.05 is 100. Log of 100 is 2. So it's going to be 0.059, right? The 2's will cancel out, and you'll do 1.1 plus 0.0592, and that would give us 1.1592, right? Which is too many sig figs anyway. But so not a big difference, but it does make a little bit of a difference there. So you can set up a cell to run just on the differences in concentration. If you do something that's just based on differences in concentration, you're going to get a very low voltage, like you did on the one on Friday, right? You had to mess with the voltages or mess with the concentrations. And if you mess with the concentrations, you can get a small voltage. It's not very much, because the standard cell potential, this would be 0. But then you would take your log part here, and that works out, right? So not a bad idea to pause me and do that. I'm trying not to take too long to do this, but you get 0.0592 divided by 2 times log of 1 divided by 0.01001. So this would be, that's the 0.0888, because that's 3 powers of 10 again, right? So it's 3 powers of 10. So still, even with 3 powers of 10 different there in our concentration, it's 0.088 volts. We will come back and hit that on Wednesday. Yeah, we'll talk work and plating and stuff on Wednesday. Anyway, keep working the owl problems, keep working through stuff. Come see me in the Google Meets if we're struggling with anything.